Runge Kutta methods are the most used explicit methods. Okay, so they don't require the knowledge of the next points, and they don't require also the calculation of the derivative of f of xy with respect to x or y, as we saw before. Okay, so basically they use higher order approximation for the integral, but they use additional approximation in order to become an explicit method. So first we're going to talk about the second order Runge Kutta method. These methods are equivalent to a second Taylor expansion method. Okay, so we have two methods which are equivalent. Okay, equivalent from the numerical point of view, I mean that the accuracy is approximately the same. Okay, we have the RK2A method. So in the RK2A method, yi plus 1 is equal to yi plus f of xi plus h over 2 yi plus h over 2 f of xy of xi yi. Okay, so the parenthesis is in front of all of this. Okay, so it's f of xi plus h over 2 yi plus h over 2 f of xi yi. The RK2B, okay, the expression reads as following: yi plus h over 2 f of xi yi. Sorry, this here there is an h over 2 h here. There's h multiply all of this, and here it's h over 2 f of xi yi plus f of xi plus 1 unit xi plus h. Okay, yi plus f of xi yi. It's quite a long expression here. Okay, so it's yi plus h over 2 multiply f of xi yi plus f of xi plus 1 and xi plus h yi plus f of xi yi. Okay, here the parenthesis is in front of all of this term, so it's f of all of this. Okay, because f is a function of two variables. And you will see how these two methods are derived. One is derived from the midpoint approximation, and the other one is derived from the trapezoidal method with an additional approximation. Okay, let's start by the RK2A, okay, and see how we can derive this expression here. So the RK2A is derived from the midpoint rectangle approximation. Okay, so basically let's rewrite yi plus 1 is equal to yi plus integral from xi till xi plus 1 of f of t y of t dt. And like I said, if I use the rectangle midpoint approximation here, then it's yi. For the rectangle midpoint approximation, I use the midpoint. Okay, so the midpoint is between xi and xi plus 1 is xi plus h over 2. Okay, because between xi and xi plus 1 there's h. Okay, now y of xi plus h over 2. Okay. Now, the y of xi plus h over 2, we need to find an approximation for this. Okay. Now, the y of xi plus h over 2, using the first order Taylor approximation, I can approximate it as y of xi plus h over 2 y prime at the point xi. So it's yf of xi yi. And now replacing this expression by this one, we get the RK2A. Now we are going to see how to derive the RK2B. Okay, so this is the expression for the RK2B. Now if we want to derive this expression, we will start from the same starting point. yi plus 1 equals yi plus the integral from xi till xi plus 1 of f of t y of t dt. Now, if we use now the trapezoidal rule, okay, trapezoidal method, and we can replace this by the mean value of xi, yi, and xi plus 1, yi plus 1. So it becomes h over 2 f of xi yi plus f of xi plus 1 yi plus 1. Okay. Now, all these terms are known except the yi plus 1. Okay. Like I said before, okay, this is an implicit method. Now, if we want to convert it into an explicit method, we need an expression for the yi plus 1 that depends on the yi. And that's what we will do. So, if we use now the Taylor expansion on first order for the yi plus 1, write yi plus 1, yani yi plus h, and yi plus 1 is y at xi plus h. It's equal to yi plus h, okay, y prime at the point xi, which is equal to f of xi yi plus h f of xi yi. Right. Now, if I replace this expression inside of this one, okay, instead of this one, I replace it by this one, we get the RK2B expression. Okay. We can write these methods in another way in order to be easier to learn. So for example, for the IK2A, you can write it as K1 is equal to h of xi yi, K2 is equal to h of xi plus h over 2 yi plus K1 over 2, and then yi plus 1 is equal to yi plus K2. And for the IP2B, you can write it the following: K1 is equal to h of xi yi, K2 is equal to h of xi plus 1 yi plus K1, and then yi plus 1 is equal to yi plus half K1 plus K2. Okay, so this is easier to learn, and it's easier to put into the program. So instead of using long expressions. Similarly, as we did before, we can derive even higher order Runge Kutta methods. Okay, the Runge Kutta method of order 4, or the RK4, which is one of the most accurate explicit methods ever used. Okay, and this method, as you expect, is derived or is based upon the Simpson method. Okay, the derivation of this method is quite long, so I will not derive this method, but basically we use the Simpson expression for the integration, and we use some approximation in order to get this expression. So the RK4 reads as K1 is equal to h of xi yi, K2 is equal to h of xi plus h over 2 yi plus K1 over 2, K3 is equal to h of xi plus h over 2 yi plus K2 over 2, and K4 is equal to h of xi plus h yi plus K3, and then the yi plus 1 is yi plus 1 over 6 K1 plus 2K2 plus 2K3 plus K4.